This screencast is going to discuss percent composition of compounds and empirical and molecular formulas. Percent composition is the percent by mass of a substance in a formula. We usually say calculate the percent by mass or calculate the mass percent of a certain substance. And for percentages, we're going to list it for the monatomic elements. For example, something like hydrogen. Hydrogen, I taught you guys as a diatomic molecule as H2. When we're asking about percent of hydrogen, we just want the monatomic element, so just percent of H. For example, I could ask you, calculate the percent H in water. For the formula of mass percent, it's the mass of an element or a substance divided by the total mass of the formula and multiplied by 100. So when it says mass of element or mass of a substance, an element could be something like hydrogen in water. A substance could be something like water in, let's say, a hydrate, in magnesium sulfate heptahydrate. For sig figs, if there are no other numbers given, then we're going to go to 2 decimal places. And if you're thinking about percent composition, if I have, let's say, percentage of hydrogen and percentage of water, both of those percentages, they should add up to 100%. One example problem would be to calculate the mass percent for each element in acetic acid. So the first thing that we have to do is we have to figure out what the formula of acetic acid is. And the formula is HC2H3O2. Then the next step is we're going to calculate the MM. So MM stands for molar mass. As you have a total of 1 hydrogen here and 3 hydrogen here for a total of 4. Then I would multiply by the molar mass of hydrogen, which you would get on the periodic table, 1.01. Then you would add that to 2 carbons and then 2 oxygens. And you get a total of 60.06, and that's grams per mole. Now we can start calculating the percent composition for each element. I'll start with hydrogen first. Okay, so with hydrogen, I'll do percent H over here, and it's supposed to be the mass of hydrogen divided by the mass of acetic acid multiplied by 100. And when we're talking about the mass of hydrogen, we're not just looking at just the monatomic hydrogen. We're looking at how much hydrogen is in the entire acetic acid, and there are a total of 4. Okay, so I'm going to do 4 times 1.01 divided by 60.06. Multiply by 100. And again, here there are no numbers given in the question prompt, so we're just going to go to 2 decimal places. And I have the answer right here. So the answer should be, after you plug it in, 6.73%, and then you put the symbol H after that. Then we can also calculate the percent composition of carbon. And you're going to do the same thing. So to figure out carbon, it would be the mass of carbon divided by the mass of acetic acid multiplied by 100. And so for carbon, it's not just 12.01, it's how many carbons you have in the entire acetic acid formula unit, and there's 2 of them. So I do 2 times 12.01 divided by 60.06 times 100, and you should get the 39.99% C. And then the last one is to calculate percent oxygen. So to calculate percent oxygen, it would be the same thing where you take the mass of oxygen, or same concept, mass of oxygen divided by mass of acetic acid, and then you multiply by 100. So here we got 2 oxygen, so it would be 2 times 16 divided by 60.06 times 100, and you would get 53.28% oxygen. And if you wanted to double check to see that your answer is okay, if you add up the 6.73, the 39.99, the 53.28, you should get 100%. And if not, then maybe you punched something in wrong in your calculator. I just wanted to show you one alternate way to calculate, let's say, oxygen. For oxygen, if I already am confident about my hydrogen and my carbon, and I know everything adds up to 100%, I could take 100% minus 6.3% for hydrogen minus 39.99% for carbon, and I should get the 53.28% oxygen. So that's just one alternate way of calculating one of the last element percentages. For this section right here, chapter 8.6 with empirical and molecular formulas. An empirical formula, if you were to define this, it would be any chemical formula with the lowest whole number ratio. And for this class, I'm going to abbreviate empirical formula as EF. And an example of An empirical formula would be something like water. Okay, so water, H2O, it has a ratio of 2 to 1. It's already the lowest whole number ratio. Definition of a molecular formula, there's actually two. So it's going to be either any multiple of your empirical formula, and I'll show you what that means in a second. And it's also the actual formula of your substance. So an example of a molecular formula would be something like C6H6. So if I have C6H6, that's called the molecular formula because you could divide both of those subscripts by 6 and you can simplify it to CH. We would call the C6H6 the molecular formula, and then we would call the CH that I simplified the empirical formula. And I guess I should mention that molecular formula I'll abbreviate as capital M, capital F. And in terms of percentages wise, if we're looking at the percent of carbon and the percent of hydrogen in your formulas, these will be the same for the molecular and the empirical formula. And so the actual formula of the substance would be C6H6, and then the empirical formula will be just CH. And then for here, I wrote it could be any multiple of empirical formula. Water. Okay, so water is an example where, okay, so H2O, this is the molecular formula. This is the actual formula of water, but it is also the empirical formula. So the multiple, when we're talking about multiple could be 1. This one, the multiple is 6, but this one could be 1. So in this practice problem here, I wanted you to identify all the empirical formulas. So for SO2, this would be an empirical formula because the ratio of the subscripts is 1 to 2. It's the lowest whole number ratio. Sodium sulfate is also an empirical formula. So you might be thinking, oh, I could divide everything by 2. Not the case because for sulfate, there's 1 sulfur, and you can't reduce that anymore. Something like glucose, though, C6H12O6 is not an empirical formula. It's a molecular formula because you could divide everything by 6. Magnesium hydroxide, this would be an empirical formula because it's already simplified. Same thing with calcium phosphide, already simplified, 3 to 2. And then the last one, acetic acid again. This one is actually a molecular formula. It's a molecular formula because if you were to consolidate the hydrogens, you actually have 4 hydrogens. So you have 4 hydrogens, you got 2 carbons, and you got 2 oxygens. So you could divide everything by 2. I'll continue the rest of the notes on another screencast.